Rates of change examples. Objective: by the end of this lesson, you should be able to read a rate of change application and extract key quantities and rates. Identify what a rate of change application problem is asking you to solve. 4. Solve a variety of application problems involving rates of change. So let's get right into it. Let's do a couple examples here. Example 1. Let x of t equal t cubed minus 3 halves t squared minus 18t plus 30. Represent the position of a particle traveling along the x-axis, where t is given in seconds and xt is given in inches. So, right, key things. So, our xt is in inches, and our t is in seconds, so it's seconds in inches. The particle is traveling horizontally along the x-axis, so that's horizontal. So we're going left and right. And x of t is our position function. Right, remember the way it goes? It goes position, velocity, acceleration. And if you want to take a derivative, go down. Right, so if you want to go from position to velocity, take a derivative. If you want to go from velocity to acceleration, you take a derivative. Position is position, velocity is movement, acceleration is like increasing your movement. Anyway, so that's the gist. Let's talk about this particular problem. Find the position of the particle at 1 second. So again, they want the position. I have the position particle. They're giving me t equals 1 second. They're giving me the time, so you just substitute it in. So x of 1 is equal 1 cubed minus 3 halves. 1 squared minus 18 times 1 plus 30. If we simplify that out, it's basically 1 minus 1 half, so 0.5. 18 plus 30, that's 12. So negative 0.5 plus 12 is 11.5. Now again, units, we're in inches, right? This is our position function, so we're just in inches. No rate, just position. So how far you are from the origin, we're at 1 second, we're 11.5 from the origin. Find the velocity at time t. So they want us to find the velocity. Well, we have a position function. To find the velocity, I just take the derivative. So my velocity function, x prime of t, which is the velocity function, is just going to be 3t squared minus, bring some down, subtract it off, 3t minus 18. This will be in inches per second. Right? It's anytime you take a derivative, it's divided by the x value. So in this case, that's time, seconds. So that's my velocity function. What is the velocity after 2 seconds? So likewise, this wants to plug 2 seconds to our velocity function. So velocity at 2 seconds, 3 times 2 squared minus 3 times 2 minus 18. So this is 4. You always do this first. So 12 minus 6 minus 18. So 6 minus 18, negative 12. Now again, we're in velocity, so it should be a rate. If it was inches, we're divided by time, so inches per second. So again, that's all it's telling us is that we're going to the left. After 2 seconds, we're moving to the left at negative 12 inches per second. So every second we're going under 12 inches. When is the particle at rest? Right? So particle at rest means it's not movement. It means it's not moving, so its velocity is 0. Right? Because it's stopped moving. So we're going to set our velocity equal to 0. Now, keep in mind, when is the particle at rest? Right? We're looking for time. When does time equal? So we're not going to plug in 0. We're looking for time. We're not going to plug in 0 for time, I meant to say, because we're looking for time. We're going to set it equal to 0. It's very important there. A lot of people mess that up. When is the particle at rest? We're looking for t. So we're going to set it equal to 0. We're going to set our velocity equal to 0. Which would give us 0 equals 3t squared minus 3t minus 18. We can make life a little easier. Notice they all divide by 3. Let's divide everything by 3. Include the 18. 0 equals t squared minus t minus 6. If we want to factor that, we get t minus 3, t plus 2. And we get t equals 3 and negative 2. Now we're talking about a rate of change problem, so time has to be positive. So in general, when we do these, time is always going to equal to 0. So right here, I got time is negative 2 seconds. We can't go back in time. No back to the future here. So time is just 3. E. When's the particle moving in the positive direction? So a couple things here. First, talk about movement. So that's velocity, right? Now in the positive direction, that means we want the velocity to be greater than 0. We want to move into the positive direction. So how do we solve this? Well, we just do what it says. We set the velocity greater than 0. So we'll use this simpler velocity equation. T squared minus t minus 6 is greater than 0. So literally just send the velocity greater than 0. Now how do we solve this though? We're talking about quadratic inequality. It's a lot tougher than linear inequality. Quadratic inequality is generally two ways about doing this. One is you graph it as you find your zeros. First, actually, we got to find our x-intercepts, or zeros, however you want to call it. So you could then after that you either graph it or you make a sign chart. I'll try to do both ways real quick right here. So if we're going to grab, well, first, either way, we got to find the x-intercepts. We actually did earlier, right? We factor it, so we got 3, -2. So you know that t equals 3 and -2 is our x-intercepts. Now, what we could do is we could graph it. All right, we know my x-intercepts are 3 and -2. It's not supposed to be a nice perfect graph. It's supposed to give you an idea of what's going on. Now, notice our equation here is a positive t, so let me just be cleaning up. Technical, but my line is to be -6 of that guy. So my graph looks like this. It wants to know when it's moving in a positive x direction. So when is my graph here positive? Well, if you look at it, it's positive right here from 3 on, when time is greater than 3. And right here, when time is less than -2, but again, we don't count negative time. So when time is greater than 3, also known as 3 to infinity. So that's how you do it by graphing. You can also do it by making a sign chart. What's that about? Well, it's kind of the same idea, but we just hit our key points here. We have -2 and 3. And what you do instead is, instead of like graphing, you just make you do little test points. So in between these values, so a little point that's higher than 3, so like 4. Points in between these two, like 0. The point over here that's less than -2, like -3. And actually, I don't even care about that. Really, since we're doing rated rates, all I care about is 0 on, honestly. But anyway, and what you do is you plug it into your equation there. See if you get a positive or negative. So if you plug in -3, -3 squared is 9, minus -3 is 12, minus 6 is 6. So I get a positive value. If I plug in 0, it's easy. Gone, gone. I get -6. So I get a negative value. And if I plug in 4, I get 16 minus 4 minus 6. So 16 minus 10, so 4. So positive value. And likewise, I want my velocity moving to the right. So I want a positive value, which is this guy right there. So again, 3 to infinity, or t is greater than 3. Again, I don't use this one because it's a negative value, so I won't use another. For that, I want only positive time. So that's how you find when a particle is moving in the positive direction. And we'll do another one like that in a second. Next, let's find the acceleration at time t. So remember, acceleration is the derivative of velocity. Up here in my chart. Right, position, velocity, acceleration. So it's like the increase and decrease in the velocity. Well, my velocity function was this. 3t squared minus 3t minus 18. My acceleration function would be the derivative of that, so 6t minus 3. That's my acceleration function at time t. And kind of like we talked about before, when is the acceleration positive? So I just want my acceleration to be greater than 0. So I'm going to set 6t minus 3 greater than 0. Now this is a linear function, so much easier to solve, a linear inequality. Right, all we're going to do is solve it basically. 6t is greater than 3, add a 3 over, divide by 6. So t is greater than 3/6, or t is greater than 1/2. And you can still solve the other way. You can still make a sign chart at 1/2 and then see which way it goes. You can still graph it if you want. It's a line. Easy enough to graph. We know how to graph a line. Y-intercept of 3, -3, and a slope of 6. And it crosses at 1/2. This be positive. Be negative. So you can still do it either way. Both ways work. So I have, when is acceleration positive? So you set the acceleration greater than 0, solve it, I get t greater than 1/2, or 1/2 to infinity. In interval notation. Next, is the speed of the particle increasing or decreasing with t equals 2 seconds? So, if you remember from before, speed's all about whether acceleration and velocity have the same sign. If they have the exact same sign, plus plus or minus minus, that means they're helping each other out. So that means it's increasing. So if they have the same sign, your speed's increasing because they're working together. They're either both going to the right or both going to the left. When they're opposite signs, one's positive, one's negative, or vice versa, then they're working against each other, so the speed's decreasing. So that asks us about at 2 seconds. So here's an easy way to think about it, easy way to do it. Just literally figure out what v of 2 is and what acceleration of 2 is. That's it. So what we get. The velocity at 2, we had an equation up here. 3 times 2 squared minus 3 times 2 minus 18. I think this one earlier, actually. Yeah, we got negative 12 meters per second from earlier. The acceleration at 2, just plug 2 into the acceleration formula. So 6 times 2 minus 3, so 12 minus 3, so 9. A positive 9 meters per second squared. Back to the acceleration. Notice they're different signs, so they're working against each other. If the velocity wants to go to the left, acceleration wants to go to the right, so we are slowing down. So speed is decreasing. Find the total distance traveled by the particle in the first 3 seconds. So this one's a little tougher. So total distance traveled by the particle in the first 3 seconds. So this is how we do this. What we want to do is look at our number line, our graph. So we start at 0. And look at all the critical points. Or zeros. Now we actually got lucky. Our only 0 was that cared was 3, right? Like here's our sign chart up there. We got negative 2 and 3. I don't care about negative 2. That happens less than 0, so it doesn't matter. Right? We start at 0 because the time starts at 0, and then we stop at 3. And what you do is, since we want the first 3 seconds, all I'm going to do is this. I'm going to find, well, since I don't have to worry about any critical points, I just got to find the distance traveled here. So how do we do that? We do this. We're going to do distance, so that's it's a position thing. So we're going to do s of 3 minus s of 0. And I got to do one last thing. I got to put an absolute value because I don't care. Distance isn't a positive, negative value. You don't say how far is the bookstore and you say negative 10 feet away. You just say 10 feet away. So distance is positive. This is a positive value. So that's what we do absolute values. All we got to do is subtract those two things. So we just put s of 3 into the equation, right? Into our position equation up here. I did it already. That's going to give us negative 28.5. We'll plug s of 0 into our equation. That's a lot easier because you just look for the y-intercept. So 30. So plug those in and we get absolute value of negative 58.5, which is just 58.5. Now keep in mind, if I'm doing units, we're talking about distance. That's a position value, so it's just the position. And in this case, we're talking about inches. So 58.5 inches is how far we travel in the first 3 seconds. That's our first example. Let's move on to the next one. Position of a particle is given by s of t equals t cubed minus 3t squared minus 6t plus 5. Where time is measured in seconds and s of t is in feet. So our position is, we're in position again, it's in feet, and then our time is in seconds. So this is in time in seconds. This is our position function in feet. Find the initial velocity. Again, notice it's velocity. That's our derivative. Right? We go from position, velocity, acceleration. So we need to take a derivative of this guy. Going to equal 3t squared minus 6t minus 6. Now notice it says initial velocity. So it's the starting time. So what's your velocity at the start? So t equals 0. So anytime you're initial, t equals 0. So initial, t equals 0 every single time. So we're just going to sub in 0. We're going to get negative 6. Now again, units is feet per second. So if we're taking a derivative, you just divide it by time. So feet per second. So negative 6 feet per second. So my initial velocity is going every 6 feet, we're going back for every 1 second. Find the velocity after 2 seconds pass. It's simple. Plug in 2. So plug into my velocity function. And actually I'm going to get, what's this, 4, so 12 minus 12 minus 6. So I'm getting negative 6 feet per second again. So it hasn't changed. Our velocity has not changed after 2 seconds. Find the acceleration after 2 seconds that pass. So here we gotta take a derivative again, right? Because again, it goes position, velocity, acceleration. Let's take the derivative of velocity. So my acceleration is going to derivative this guy right here. So 6t minus 6. Let's plug in 2. So the acceleration of 2 seconds is 6 times 2 minus 6. So 12 minus 6, which is just 6 feet per second squared. So that's our acceleration after 2 seconds has passed, right? So we just plug into the second derivative. So this says that our acceleration of our velocity is increasing at 2 seconds, about 6 feet every 2 seconds squared, every second squared. The next example, more up and down. If a stone is thrown vertically upward from a surface of a known planet, its height in meters after t seconds is given by this. Now see the little GC here? That means graphical display calculator. So maybe we get to use a calculator on this one. So anyway, here's our height. That's our position function. And the problem wants to know, what is the velocity of the stone after 1 second? So again, I need to find velocity. Remember, it goes position, velocity, acceleration. So I gotta find the velocity, so I gotta take a derivative of this guy. So h prime of t, which is my velocity, is just 10 minus t, if I did that math correctly. And after 1 second, you just plug in 1. 10 minus 1, so 9. What's my units here? Seconds and meters. I should have wrote that down here. So 9 meters per second. B, what is the velocity of the stone after it has risen to 18 meters? So keep in mind, we want to know what the velocity it is, but we want to know what the velocity is when it's gone up to 18 meters. So this right here is the position question. When is it at 18 meters high? So like, when does it hit right there-ish, right? It's 2 points. So it's those two values. So what I gotta do is set my velocity equal to my position equal to 18 meters, right? This is a position thing. So I'm gonna set my position equal to 18 meters. That's my height. So we're gonna go 18 equals 10t minus 0.5t squared. So I know what you're thinking. Oh, I gotta solve that. I guess it equals 0 and factor, use quadratic formula. Normally, yeah, but we do get to use a graphing calculator. So let's plug into our calculator. I had that a little bit off screen already. Right, so I went to y equals, typed it all in. Remember, we don't have a t, so we just use x. You hit graph. Now, I really can't see it. I gotta fix my window a bit. So I'm gonna hit window. My max height is 18, so I'm gonna change my y max to like 20, so I can see it a little better. Use into this effect. See, there's the line 18. And then that crosses, and I gotta go more right, because I can't see anything right now. Actually, let's look at the graph right here that they gave me. I should go to at least 20. So let me go to like 25 to give myself a little buffer. Right, my x max here is a little high. So then it's this effect. So there's a graph. It crosses there and there, so let's find those. So we'll go second, calculate intersects. I just want to get close to the two sides, figure out what those values are. Hit enter a couple times, and I get 2. That's interesting. Because I could have solved it by hand. And then I guess find the other one. Do the same thing, but on this side. And we're gonna get the entry of 18. So at 2 and 18 is when the particle is at 18. But remember, the question wasn't that. It was what's the velocity. So I gotta find out what v of 2 is and what v of 18 is. V of 2 is just gonna be 10 minus 2, which is gonna be 8 meters per second. V 18 is gonna be 10 minus 18, so negative 8 meters per second. And that makes sense, right? At 2 seconds, I'm increasing speed. We're going the stone is going up to positive slope, so positive 18 meters per second. At 20, my stone's going down, so the slope is negative, right? So it's falling, so negative 8 meters per second. So it makes sense. When does the ball hit the ground? So again, hit the ground, that's a position thing. Ground's always position, so position equals 0. So I get to set 10t minus 0.5t squared equal to 0. Again, I can solve this with my calculator, find the zeros, or x, just find the x-intercept right there. But this is the easiest to solve. I can factor out a t from both sides, and I get 10 minus 0.5t equals 0. Split it, t equals 0, which we already knew. and 10 minus 0.5 t equals 0. Just do some math. And t equals 20, which you could see by from the graph. So that's when the ball hits the ground. So again, notice it says when, so I'm looking for time. This one asks what the velocity was, so I was looking for velocity. So once I found my time, I decided to do an extra step to find velocity. What is the speed of the ball when it hits the ground? So again, speed is velocity, and actually speed is the absolute value of velocity. Speed doesn't care, there's a slight difference. Right? Velocity tells you which direction, that's why it has a plus and minus. Speed doesn't care. If I said what's the speed of the ball at 18, it would just say 8 meters per second. What's the speed of the ball at 2? 8 meters per second. Speed is absolute value of velocity. It doesn't care about which way you're going, just how fast you're going. So we're going to take the velocity at 20. That's what we found. Absolute value of that. So that's going to be absolute value of 10 minus 20, which would be absolute value negative 10, which would be 10 meters per second. So again, the velocity at 20 was going down like negative 10 meters per second, but speed doesn't care about that. Speed just cares about what's going on, like how fast are you going. So there's that idea. So one last one. The position of a particle is given by the equation S of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds at their s meters. What is the velocity after 2 seconds, after 4 seconds? So again, I got to find the velocity. And remember, like we talked about many times, it's position, velocity, acceleration. So right now I have the position function. In this case, it's an s. So let's take a derivative, find velocity. My velocity equation is going to be 3t squared minus 12t plus 9. So let's find the velocity at 2 seconds. V of 2, just plug that in. So I'm going to get for 12 minus 12, negative 12 plus 9 is negative 3. We're in meters per second. I should always write this down. Seconds and meters. So meters per second. So that's my velocity at 2. Velocity at 4. And you plug that in. You get 9 meters per second. And again, that's my velocity at 2. Right? Should make sense. We should be going down. My velocity at 4 should be going up. And that doesn't make sense. We're going up 9 meters per second. I have a steeper slope too. Notice that, right? The slope is steeper, so that's why I have a higher velocity. When is the particle at rest? Right? So again, particle at rest means it's not moving, so the velocity equals 0. So we're going to set our velocity equation right there, equal to 0. Luckily for us, again, they're all divisible by 3, so we divide everything by 3, we get t squared minus 4t plus 3. And we can just factor that to get t equals 0 equals t minus 3, t plus 1, minus 1, t minus 3, t minus 1. So we get t equals 3 and 1. It should both be negative. So 3 and 1, which is when it's, if you look at our graph here, right, it's at its peak in values, right, which is also when the velocity stops moving, right? For a split second before it goes from upward to downward, it stops moving. With the particle moving forward, so we're going to set our velocity greater than 0. So remember, there's 2 ways to do this. I can make a sign chart, or I can just graph it. The graphing is the faster way if you know how to graph it. So, right, I know I cross at 3 and 1. So here's 1, here's 3. And now if we look at our equation, our velocity equation here, it's a positive, so that means it opens on the top right. So it opens on the top right, or opens up, I should say. So it looks into this effect. Right, so it's positive, so it opens up. I know my x-intercept, so I get that. And all we got to decide is where is it positive. So it's where it's greater than the x-axis. So right here. So from 3 to infinity. And right here is my graph above the x-axis. Now remember, we don't do negative time, so that'll just be from 0 to 1. So velocity is moving forward from 0 to 1. Union 3 to infinity. Is a particle speeding up or slowing down at 2 seconds? So remember, speeding up and slowing down, that's when velocity and acceleration are either working at this together, plus, plus, minus, minus, that's when it's speeding up. Or if they're working against each other, plus and minus, either vice versa, then slowing down. Easy way to test this is just find out what v2 is and a2 is. So velocity at 2 and acceleration at 2. Velocity at 2, I already have my equation. So 3 times 2 squared minus 12 times 2 plus 9, which we did earlier. We got negative 3 meters per second. I still got to find my acceleration. I haven't found it yet. So let's take a derivative of that guy. So remember, acceleration is derivative of velocity. I have my velocity. So my acceleration is 6t minus 12. So let's plug 2 into there. So I get 12 minus 12, which is 0 meters per second. Now here's the thing. So is that increasing or decreasing? Well, this is negative. 0 has no value. It's neutral. It's not positive or negative. So remember, it's only if they're both positive or both negative, or same signs or different signs. This is kind of a mix. It's a negative and no sign. So that means neither. It's neither increasing or speeding up or slowing down at 2 seconds. Okay, last one. Find total distance traveled during the first 4 seconds. So if we look at our graph up here, right, our particle is starting at 0. It's going positive to 1. Then it's going negative until 3. And then it's going positive all the way up. And all I care about is the first 4 seconds. So what I got to do here to find total distance traveled by the particle in the first 4 seconds is to break it up. I got to figure out the distance traveled in this little stanza. So the way you do that is just s of 1 minus s of 0. Absolute value, because I don't care if it's positive or negative. Plus, I got to find the distance traveled in this little stanza. So all we can do there is s of 3 minus s of 1. When we're doing s, because that's position. Right, what's the position? What's the position we were at 3 minus what's the position we're at 1? So that's the distance traveled between 3 and 1. What's the position we're at 1? What's the position we're at 0? And the same thing for the last one. Right, plus distance we traveled from 3 to 4. So s of 4 minus s of 3. That's the distance we traveled from 3 to 4 seconds. Now if you plug into your calculator, the value just be 4, negative 4, plus 4. So that's 4 plus 4 plus 4, which is 12. Now again, it's distance traveled, so it should be a quantity, not a rate, so it's just meters. So let's go over that again. So a lot of people have a hard time with that. The general idea is this. Now I want you to find total distance traveled. All you got to figure out, so you start at 0, figure out all times it changes direction. So in our case, right, when did it stop moving? Stop moving from 1 and 3. That's when the velocity equals 0. So you find these critical points. So every time you stop, and all you gotta do is find the distance traveled in each of those points. So distance traveled between these two. And the way you do that is s of a minus s of 0 plus the distance traveled in the middle points. So that'd be s of b in my case minus s of a plus the distance traveled in the final. So s of c minus s of b. And then we do opposite value for all these because we don't care if it's positive or negative. We just want the distance traveled. We don't care which side they're going. And that's how I find those total distance traveled. You find the critical points, break your graph from those critical points, and find the distance traveled in each of those little stanzas. That's it.